Our galaxy holds billions of stars and likely billions of planets. The challenge is locating the specific Earth-sized worlds orbiting sun-like stars when they are completely swallowed by the blinding light of their host star across light years of space. The European Space Agency engineered a dedicated observatory to solve this exact problem. It is called the PLATO mission. The name stands for Planetary Transits and Oscillations of Stars. To find these distant worlds, the spacecraft will not capture direct photographs of them. Instead, it relies on detecting nearly imperceptible shadows and vibrations radiating through deep space. Before searching the cosmos, the hardware must prove it can survive both the violence of a rocket launch and the punishing environment of orbit. This requires a meticulous assembly process where engineers integrate the thermal sunshield and the deployable solar panels that will power the instruments. Once assembled, the entire structure is subjected to acoustic and vibration tests, blasting the hardware with deafening noise to mimic the intense physical stresses of liftoff. The spacecraft then moves into the large space simulator. Here, it is sealed inside a massive cryo-vacuum chamber and exposed to the total vacuum of space, while liquid nitrogen drops the operating temperature down to -80 degrees Celsius. The rigorous testing schedule keeps the mission on track for an anticipated launch between 2026 and 2027, flying aboard an Ariane 6 rocket. Passing these brutal exams guarantees the optical equipment will function flawlessly once deployed 1.5 million kilometers from Earth at Lagrange Point 2. Most space telescopes rely on a single massive mirror to gather light. PLATO breaks from this design, utilizing an array of 26 individual cameras. This divides the optical labor. 24 normal cameras operate together to observe incredibly broad fields of stars, while 2 fast cameras focus strictly on the brightest stars and feed precise pointing data to the spacecraft's attitude control system. This celestial plot shows how those camera views overlap. By grouping the lenses this way, the spacecraft achieves an enormous field of view, allowing it to monitor over 200,000 stars simultaneously. Because a planet crossing in front of its star is a rare and fleeting event, this massive simultaneous monitoring is the only statistical way to guarantee we actually catch it happening. PLATO relies on the transit method, detecting unseen planets by measuring the tiny dimming of starlight when a planet crosses its star. The dip's depth reveals the exoplanet's physical size. By recording repeated transits, scientists establish the exact orbital period. However, simply spotting a transit in a habitable zone only gives us the planet's size and its orbit. That data alone does not prove the planet is actually habitable. To truly understand an exoplanet, scientists have to look closely at the star it orbits. You cannot characterize the planet without first characterizing the host star. This brings us to the O in the PLATO acronym, astroseismology. This is the study of stellar oscillations, commonly known as starquakes. Stars are constantly resonating with internal acoustic waves. By measuring the extremely subtle vibrations in a star's brightness caused by these waves, scientists can calculate the star's exact mass, radius, and age. Because planets form alongside their stars, determining the precise age and size of the host star immediately locks in the exact age and size of the planet orbiting it. Knowing the size and age of a planet is a significant step forward, but we are still missing one critical metric needed to define a true Earth twin: planetary mass. For this, the mission relies on Earth-based observatories conducting ground-based radial velocity measurements to assist the space-borne telescope. Radial velocity detects the microscopic gravitational wobble of a star as it is pulled by an orbiting planet. By measuring that wobble, scientists can calculate the mass of the unseen world. The transit provides the physical size, while the wobble reveals the mass. Integrating both datasets is the only way to determine a planet's true composition. When we combine the mass data from the ground with the size data from PLATO, we get the planet's density. By taking that calculated density and pairing it with the host star's temperature, astronomers can accurately map out the Goldilocks habitable zone, where liquid water could exist on a rocky surface. PLATO will not definitively discover alien life. What it will do is build humanity's first reliable, large-scale catalog of well-characterized rocky planets. By confirming the density, age, and orbits of these worlds, Plato's ultimate legacy will be revealing whether planetary systems like our own are a cosmic norm or an extreme rarity.